Hello everyone, good evening. This is Vignesh, working as an assistant professor in SNS College of Engineering, Coimbatore. Okay, so in my previous video, we have talked about the problems in engineering thermodynamics. We have discussed some important topics around the work done by the system and on the system, the difference between work done by the system and on the system, then the difference between the heat transfer to the system and by the system. Okay, so and then we have seen two problems, and the continuation of these two problems will be a problem number 3. Okay, so 0.3 kg of nitrogen gas at 100 kilopascal and 40 degrees centigrade is contained in a cylinder. Okay, the piston is moved compressing nitrogen until the pressure becomes 1 megapascal and temperature becomes 160 degrees centigrade. The work done during the process is 30 kilojoule. Okay, calculate the heat transferred from the nitrogen to the surroundings. This is the important thing. Heat transferred from the nitrogen to the surroundings. Okay, then you have to take CV value. Okay, coefficient, right? So CV value is as for nitrogen as 0.75 kilojoule per kg Kelvin. Okay, so this is the piston cylinder arrangement where nitrogen is there. Okay, the properties of nitrogen gas is given, that is mass is 0.3 kg and pressure is 100 kilopascal and the temperature is 40 degree centigrade. Okay, so where the piston is moved in order to compress that nitrogen. Okay, so we are giving work to that system. Okay, we are moving the piston so that we have to give a work. Okay, so the pressure becomes 1 megapascal. Initially it has been 100 kilopascal. Once we compress the nitrogen gas, the pressure becomes increased, so it will becomes around 1 megapascal and the temperature becomes 160 degrees centigrade. Okay, so we have given the work done, right? Work done during the process is 30 kilojoule. Okay, calculate the heat transfer from the nitrogen to the surroundings. This is what they have asked. So first write down the given data. The temperature has been given, that is 40 degrees centigrade, convert it into a Kelvin. Then after the compression, the temperature has been increased to 160 degrees centigrade. Then convert it into Kelvin, that is 433 Kelvin. Okay, you have to add 278. So if you want to change the unit to degree centigrade to Kelvin, you have to add 278. So 40 plus 278, 273. I'm so sorry, 273. Okay, so 273 we have to add, so that is 13 Kelvin. Okay, and the work done during the compression process, because we are giving the work to the system, right? So that will be considered as a negative one, so that is minus 30 kilojoule. Okay, so you have to consider the heat transfer. So what will be the formula for heat transfer? That is Q is equal to W plus del U. According to the first law of thermodynamics, you know that Q is equal to W plus del U, where here they have asked the heat transfer, then you have to rearrange the formula. Okay, so U is equal to mCV into del T. Okay, so this is the formula. So if you apply that instead of U, if you apply for that equation mCV into del T, so what the equation rearranges as mCV is a common term, you have to take away as a common one, then T2 minus T1 will be there. So Q is equal to mCV into T2 minus T1 plus the work done. Okay, so substitute these given properties in that equation. You will be getting a minus 3 kilojoule. So the heat has been rejected. Yes, that is the question. In question itself, the heat is moved from the nitrogen to the surroundings. Okay, so that the answer will be in a negative one. Okay, so 3 kilojoule of energy has been transferred during this process. Okay, compression process. So this is the heat transfer to the surroundings. Okay, this is the answer. So next problem, we will see about the next problem. So a mass of 2 kg of air is compressed in a quasi-static process where PV is constant. Okay. Due to the compression, the pressure is raised from 0.1 megapascal to 0.7 megapascal. Okay. So the initial density of air is 1.16 kilogram per meter cube. Okay. Find the work done by the piston to compress the air. Okay. So there is a piston, cylinder piston arrangement is there. Inside that cylinder we are having 2 kg of air. Okay. So it has been compressed. It is a quasi-static process where PV is equal to constant. Due to the compression, right, initially the pressure is 0.1 megapascal. Due to the compression, the pressure has been increased as 0.7 megapascal. Okay, the density has been given. What we need to find is, we have to find the work done by the piston to compress the air. So PV is equal to C means it is a constant temperature process. Okay. So during this compression process, the temperature remains the same, only the pressure has been changed. Okay. So here the pressure is given as a megapascal. You have to convert it as kilonewton per meter square. So 700 kilonewton per meter square. Okay. Then megapascal, then mega means 10 to the power of 6. So 100 kilonewton per meter square. Here 700 kilonewton per meter square. Mass has been given as 2 kg. The density has been given for the air 1.16 kg per meter cube. We have to find out the work done. Okay. So for constant temperature process, the work done formula is PV ln V2 by V1. Okay, this is the work done formula for the constant temperature process. This constant temperature process, there are several processes are there: constant temperature, constant pressure, constant volume process. So there are a lot of processes are there. I will put a separate video for that. Okay, so here you have to know, what you want to know is the constant temperature. The work done formula for constant temperature process is PV ln V2 by V1. Okay, here we know this density, that is mass by volume. The density has been given. Okay, then mass by volume, we once the piston is compressed, there is a change in volume, right? Okay, so density, you have to find out the V1 with the help of density and mass. So V1 is equal to 1.72 meter cube. Okay, so this is the initial volume before compression. Then the formula PV is constant, right? So P1 V1 is equal to P2 V2. There is a 2 stages are there, initial stage and final stage. So P1 V1 is equal to P2 V2. We have to substitute the P1 V1 and P2 values in order to get the V2, that is volume at the end of the compression. Okay, so if you substitute these values, you get that is volume at the end of the compression is 0.246 meter cube. So there is a change in volume, right? So V2 is lesser than the V1 because during the compression process volume get reduced. Okay, so that V2 is 0.246 meter cube. Now substitute these values in the work done formula. Okay, so P1 V1 ln V2 by V1. Okay, so here V1 has been found out that 1.724 meter cube, V2 has 0.246 meter cube. Already pressure has been given, that is 100 kilonewton per meter square. So substitute all these values in the equation, you get the work done value. So that will be under -1. So what it means, if the work done is negative, you are giving some work to the piston in order to compress the air. Okay, so that is the value. Okay, work done. So 335.67 kilojoule of energy is work we are giving in order to compress the piston. Okay, so that's it about today. Thank you for watching.